You pick up two magnets and push them toward each other. Before they touch, there's this invisible something pushing back against your fingers. Flip one around, and suddenly they snap together with a surprising force, enough to make your fingers sting. What is that? What's really happening in that moment? It seems simple on the surface, just magnets attracting or repelling each other, but if you stop and ask why, you quickly discover that it's not simple at all. Whenever you start asking why about anything, you quickly realize you need something to stand on, a foundation of facts you already accept as true. Without that foundation, you fall into an endless loop of questioning. You ask why, get an answer, then immediately ask why again and again and again, deeper and deeper, until the process threatens to collapse under its own weight. Curiosity is wonderful, but unanchored curiosity is exhausting. Let me illustrate this. Suppose someone asks why your Aunt Minnie is in the hospital. You respond, she slipped on ice and broke her hip. That's straightforward. But if the questioner presses further, why did she slip? You might say, because ice is slippery. Everyone understands that intuitively, but why is ice slippery? Suddenly, it's not obvious. The reason is fascinating. When a person stands on ice, the pressure of their weight slightly melts a thin layer at the surface, creating a microscopic film of water. In other words, you're not sliding on ice itself, you're sliding on water. But then you could ask, why does pressure melt ice in the first place? It's because water is unusual. Unlike most substances, water expands as it freezes. Pressure tries to reverse that expansion, creating a tiny layer of liquid. And then you might ask, why does water expand when it freezes, unlike other materials? That question leads into chemistry, molecular structure, and even the behavior of hydrogen bonds in water molecules. And finally, if you return to Aunt Minnie, you might ask, why did she fall when she slipped? That's gravity pulling her down. And why does falling hurt? Because of energy transfer and force applied to bones and tissue. And why did her husband call the hospital? Presumably because he cares about her, though not all spouses respond the same way. Maybe he was angry or inattentive. The answer depends on human behavior, psychology, and social norms. See what's happening? Every answer leads to another question. If you keep asking why, you'll never stop. You need to stop somewhere, or you will collapse under the weight of infinite curiosity. Most people don't realize that this is the nature of understanding. To make sense of the world, you must pick a foundation, facts, principles, or observations you accept as true, and then reason upward from there. Without that, every why becomes just a fall through space. Now, when people try to explain something unfamiliar like magnets, they often resort to analogies, things they already understand. Rubber bands, for example. Some might say, magnets attract and repel like invisible rubber bands connecting them. At first, this seems satisfying, but if you ask, why do rubber bands pull back? You end up back at the same problem. The force is due to interactions between molecules, which are ultimately electrical in nature. And if you try to explain those interactions with another analogy, you're simply running in circles. You're using one mystery to explain another, and that is not understanding. That is a con game. The truth is, electrical and magnetic forces are fundamental. They are among the basic building blocks of reality. They do not require a deeper explanation in terms of something else. Instead, everything else, chemistry, biology, even the solidity of everyday objects, derives from these forces. Chemistry, for instance, is nothing more than electromagnetic interactions between atoms. Biology emerges from chemistry because molecules interact through electromagnetic forces to create proteins, DNA, membranes, and cells. The chair you're sitting on is solid because of electromagnetism. Your body doesn't collapse because electromagnetism holds your atoms together. These forces are everywhere. They are universal. They run everything. Here's something striking. Think about touching a table. You push on it, it pushes back. You've done this your whole life, and it feels completely ordinary. You might even assume your hand is actually touching the table, but physically speaking, it isn't. On the atomic level, the surfaces of your hand and the table never truly meet. As atoms get close, the electrons in each object repel each other due to their electric charge. That repulsion is what you feel as solidity. The table is solid because the electrons resist overlap. That's exactly the same fundamental force you feel when pushing magnets together. So why does a table feel ordinary while a magnet feels mysterious? Simply because you interact with tables daily and take them for granted. You rarely, if ever, push magnets together with the same intensity or curiosity. The table is just as strange as the magnet. You've just stopped noticing it. Electromagnetic forces are unimaginably strong compared to gravity. To give you an idea, gravity is the weakest of the fundamental forces. Electromagnetism is stronger than gravity by roughly a factor of 1040, 1 followed by 40 zeros. That's an almost incomprehensible difference. If gravity is the tiny nudge keeping planets in orbit, electromagnetism is the titanic force that sculpts molecules, builds stars, and defines chemistry. Yet we rarely notice this immense power in everyday life because, at the atomic level, the positive and negative charges in matter balance each other out. In a neutral object, the repulsive and attractive forces cancel almost perfectly. The universe hides its might in plain sight. When you comb your hair and pick up a few stray bits of paper, you've likely rubbed electrons off your hair. That tiny imbalance creates observable forces across the room, and magnets are special because, in materials like iron, electron spins align. Normally, electrons spin in random directions, so their tiny magnetic effects cancel out. In iron, they coordinate. When many electrons cooperate, the combined effect becomes large enough for us to feel at a distance. That's why iron is magnetic and copper is not. Copper has the same electrons, the same physics, and the same underlying forces, but its spins are chaotic and cancel out. It's like a stadium of people. If everyone talks at once, you hear a cacophony. If everyone chants the same word, the sound carries for miles. Alignment matters. Coordination matters. At the deepest level, what's happening when two magnets attract or repel is this. Electrons aren't stationary. They exchange tiny packets of energy called photons. Not the light we see, but virtual photons, which exist only during the interaction. One electron emits a virtual photon, another absorbs it. This continuous exchange is what creates the push or pull you feel. Every time you press two magnets together, trillions upon trillions of these exchanges are occurring, all around the electrons in each piece of metal. Remarkably, the complex phenomena of electricity, magnetism, chemistry, and even biology emerge from just three fundamental actions. A photon moves from one place to another. An electron moves from one place to another. An electron emits or absorbs a photon. That's it. From these three simple processes, the universe builds atoms, molecules, cells, and life itself. There are no hidden gears, no unseen machinery. This is reality at its most fundamental level. What makes it even more extraordinary is the accuracy with which we can predict electromagnetic phenomena. Using these principles, calculations can match experimental measurements to 10 decimal places or more. That's the difference between measuring the distance from Los Angeles to New York with an error smaller than the thickness of a human hair. This is precision unparalleled in any other field of science. It's not speculation, it's experimental verification. If it matches observation, it is correct. Yet even here, mysteries remain. There's a dimensionless number, approximately 1137, known as the fine structure constant, which dictates the strength of electromagnetic interactions. No one knows why it has this value. We measure it, we use it, we rely on it. Change it slightly and atoms would behave differently. Chemistry might fail. Life itself could be impossible. The universe as we know it depends on this number, but the origin of 1137 is still unknown, a fundamental mystery. Quantum mechanics adds another layer of strangeness. Electrons do not behave like tiny balls orbiting the nucleus, nor do they behave like clouds of fog or waves in water. Any intuitive picture we try to impose is only a metaphor, an approximation. The true behavior is captured only in mathematics. Equations predict outcomes, probabilities, and interactions with astounding accuracy, but they do not offer a visual or tactile mental image. Our intuition, evolved for human-scale phenomena, fails entirely at the quantum level. And this is crucial. Physics is not about understanding everything perfectly. It's about knowing enough to make predictions, test them, and apply them. We understand electromagnetism well enough to build power plants, motors, lights, and computers. We don't need perfect intuition, we need predictive power. That's how the dam at the hydroelectric plant spinning copper coils generates electricity for an entire city. We understand electromagnetism well enough to make it work reliably, even if we can't picture every electron's path. So when you asked why magnets attract, the desire for a simple analogy, rubber bands, springs, invisible strings, is natural but backward. Magnetism is not explained by these things. Rather, these macroscopic phenomena exist because of magnetism. Every force, every bond, every reaction stems from electromagnetic interactions. Every touch you've ever felt, every object you've held, every wall you've leaned on, every color you've seen, all of it is electromagnetism in action. You've been immersed in it your whole life. The only difference with magnets is that they make the invisible visible. They make the underlying force palpable. Every time you push a magnet, you are experiencing the same force that holds your body together, drives chemical reactions, and governs the behavior of the universe. Understanding it isn't about finding a familiar analogy. It's about recognizing that magnetism is part of the foundational fabric of reality, the same force from which everything else emerges. It's not mysterious, it's the explanation itself. It's incomprehensibly, absurdly stronger. So why don't we notice? Because atoms are balanced. Positive charges in the middle, negative charges around the outside, plus and minus, everything neutralizes. The most powerful force in nature hiding in plain sight because it cancels itself out. When you comb your hair and pick up bits of paper, you rubbed off a few electrons, just a few. But the force is so gigantic that even that tiny imbalance creates something you can see across the room. And magnets are special because of what happens in iron. Electrons spin, they all spin. And in most materials, they spin every which way. Chaos. It all cancels. But in iron, they line up, all spinning the same direction. And when they cooperate like that, all those tiny magnetic effects don't cancel anymore. They add up, they amplify, and suddenly you've got something you can feel from far away. That's why iron is magnetic and copper isn't. Copper has the same physics, same electrons, same forces, but the spins point randomly. In iron, they work together. It's like a stadium full of people. If everyone talks at once, you hear noise, nothing. But if everyone chants the same word, you hear it miles away. Same voices, completely different effect. Now let's go deeper. What's actually happening when two magnets pull toward each other? The most fundamental level, it's about particles being exchanged. See, electrons don't just sit there. They're constantly throwing things at each other, photons, little packets of light, and I don't mean light you can see. These are what we call virtual photons. They exist only during the interaction. You can never catch one and look at it directly. One electron throws a photon, another electron catches it. And that exchange is what we experience as the electromagnetic pull. It sounds strange, right? Two things pushing or pulling each other by throwing stuff back and forth. But that's exactly what's happening. Every time you feel a magnet push against another magnet, trillions upon trillions of these virtual photons are being exchanged between the electrons in both pieces of metal. And here's the beautiful thing. Everything electromagnetic comes from just three simple actions. A photon goes from one place to another. An electron goes from one place to another. And an electron emits or absorbs a photon. That's it. Three actions. And from those three actions, you get all of chemistry, all of light, all of magnetism, all of electricity, radio waves, the colors you see, the fact that your hand stops at the table instead of going through it, all of it. There are no gears underneath, no hidden mechanism. Don't ask, but how does it really work? Because this is how it really works. Photons being exchanged. That's the bottom. That's as deep as it goes. Now, people figured out the complete mathematics for electricity and magnetism in 1873. Maxwell wrote down the equations that unified the whole thing. And this was probably the most fundamental transformation, the most remarkable change in human history, because once you understand that electrical and magnetic forces are connected, that they're really two aspects of the same phenomenon, you can do things. You can make a current in a wire create a magnetic field. You can move a magnet near a wire and create a current. Back and forth, electricity and magnetism dancing together. Think about what that means. There's a dam somewhere. Water falls, turns a big wheel. That wheel is connected to copper wire spinning near some iron. And because the copper moves near the iron, electrons start moving in the wire. That movement travels through thin copper lines spread across the whole city. And at the other end, H, another piece of copper and iron, turns that electron movement back into spinning motion. All the wheels in the city turn because one wheel at the dam turns. Stop that one, they all stop. Start it again, they all start. And what's doing this? Just copper and iron, nothing else. It's not complicated machinery. It's not some special substance. It's just the fundamental nature of electromagnetism. You move iron here, iron moves over there, far away, connected by nothing but copper wire. What a fantastic thing nature is. We built everything on this. Lights, machines, all of it running because electrons dance through wires. Now here's something remarkable. We can calculate how magnetic an electron is. Not guess, not estimate, calculate using just those three simple actions. Photon goes here, electron goes there, electron absorbs photon. You add up all the ways these things can happen, all the different paths, and you get a number. And when you measure what nature actually does with very precise instruments, the theory and the experiment match to an extraordinary degree. The difference between prediction and measurement is so tiny, it's like measuring the distance from Los Angeles to New York and being accurate to less than the thickness of a human hair. That kind of precision doesn't happen anywhere else in science. This is the most accurate prediction humans have ever made about anything, and it comes from understanding the electromagnetic force. Yeah, the same force you felt as a kid pushing two magnets together. So we can describe magnetism with extraordinary precision. We can predict exactly what it will do, but can we explain why it exists in terms of something more familiar? No. And that's not because we failed. That's because electromagnetic forces are the familiar thing that explains everything else. Now there's a number in physics that nobody can explain. It's about 0.085, or if you flip it around and square it, you get roughly 137. This number determines how strong the electromagnetic force is, how strongly magnets attract, how much electrons repel each other. Everything about electricity and magnetism depends on it. And nobody knows where it comes from. We didn't calculate it from something deeper. It just is that number. If you ask why 137 and not 250, there's no answer. It's one of the great damn mysteries of physics. Where did this number come from? Did somebody write it down? And we just don't know how. If that number were very different, magnets would be stronger or weaker. Atoms wouldn't hold together the way they do. Chemistry would change completely. We probably wouldn't exist. The whole universe, including every magnet you've ever touched, depends on this mysterious 137. Now, I have to tell you something about the history, because when physicists first tried to calculate magnetic properties of electrons using quantum theory, they got nonsense. Infinity. The equations gave infinity. That's not an answer. And for years, people struggled with this. Then around 1948, a solution appeared. The idea is that we never measure a bare electron by itself. What we measure is always the electron plus all its interactions, all those virtual photons being exchanged. So you start from what you actually measure, and the infinities get absorbed into those measured quantities. Everything comes out finite. It's called renormalization. Some people think it's suspicious, like hiding problems, but the results match experiments to incredible precision. So maybe that's just how nature is. Now here's something about understanding magnets at the deepest level. The way quantum mechanics works, it's nothing like everyday experience. Your brain evolved to understand rocks and trees and animals, things at human scale. But electrons don't behave like tiny balls. They don't orbit the nucleus like little planets. People say electrons act like waves. Not exactly. Like particles. Not exactly. Like a fog. No, that's not right either. If you want a clear picture of what's happening inside a magnet at the atomic level, something you can visualize, I can't give you one. Nobody can. What we have is mathematics. We write equations, we calculate, and predictions match reality with extraordinary accuracy. It's like a machine that calculates exactly when something will arrive somewhere. It does the arithmetic perfectly, gives exact answers, but has no picture in its head. It doesn't know what anything looks like. It just calculates. We calculate what magnets will do. We're extraordinarily good at it, better than almost anything else in science. But the intuitive picture, the ability to really see what's happening, that's beyond us. Nature at that scale is genuinely different from anything we evolved to understand. And that brings us back to where we started. You push two magnets together, you feel that force, and you ask, what is that? And the honest answer is, it's electrons exchanging virtual photons. It spins lining up in iron. It's the electromagnetic force that holds your entire body together and runs the whole universe. We can describe it with spectacular precision. But if you want me to explain it in terms of rubber bands or springs or something you already know, I can't, because those things are explained by electromagnetism, not the other way around. Magnetism isn't the mystery that needs explaining. Magnetism is the explanation. Magnetism isn't some strange, isolated phenomena. Electromagnetism isn't some obscure or secondary phenomenon. It's one of the fundamental forces of nature. It's woven into everything you experience, whether you notice it or not. Every atom in your body is bound together by electromagnetic interactions. Every chemical reaction from digestion to thought depends on it. When you see color, you're witnessing electromagnetism in action. When you feel the solidity of a table beneath your hand, that sensation is electromagnetic. When a compass needle aligns itself with the earth, when an electric motor spins, when a light turns on, each of these is a different expression of the same underlying force. What's striking is how simple the foundation really is. At the deepest level, electromagnetism comes down to just three basic processes. First, a photon travels from one place to another. Second, an electron moves from one place to another. Third, an electron emits or absorbs a photon. That's it. No hidden machinery, no tiny gears turning behind the scenes. Those three actions, endlessly combined and recombined, give rise to chemistry, biology, materials, electricity, light, and the structure of matter itself. From this minimal toolkit emerges the complexity of the world. Molecules form because electrons arrange themselves in stable patterns governed by electromagnetic rules. Chemical bonds exist because of how electrons interact with one another and with atomic nuclei through this force. Life itself, DNA replication, nerve signals, muscle contraction, is a vast symphony of electromagnetic interactions playing out at different scales. There isn't a deeper mechanical explanation waiting underneath these processes. This is the level at which nature operates. What makes this even more remarkable is how precisely we can calculate the outcomes. The mathematical framework describing electromagnetism, quantum electrodynamics, has been tested again and again, and it agrees with experiments to an astonishing degree. Predictions match measured values to 10 decimal places. That level of accuracy is almost absurd when you think about it. It's like measuring the distance from Los Angeles to New York and being accurate to the width of a human hair. This isn't philosophical speculation or poetic metaphor. This is experimental science at its most rigorous. If the equations match reality and experiments confirm them, then the theory is right, at least within its domain. Does that mean we understand everything? Not even close. There are still deep mysteries embedded in the equations themselves. Take the number 137, for example, the approximate inverse of the fine structure constant. It's a dimensionless number that controls the strength of electromagnetic interactions, and nobody knows why it has the value it does. It simply appears in the theory and in experiments unexplained. We also don't have a clear mental picture of what electrons really do at the quantum level. We can write down equations that predict their behavior with extreme accuracy, but any visual or intuitive image we use, waves, particles, clouds, is only an approximation. That's an important point. Physics doesn't require perfect understanding in a human, intuitive sense. Nature doesn't care whether we can picture what's happening. Physics is, at its core, an experimental discipline. You don't sit around waiting until every mystery is resolved or every concept feels intuitive. You learn enough to make reliable predictions. You test those predictions. If the results agree with experiment, you move forward and use that knowledge. That's why modern technology works. Power plants, electrical grids, computers, medical imaging, communication networks, all of it depends on electromagnetic theory that we understand well enough, even if not completely. That dam with coils of copper wire generating electricity and sending power across an entire city works because our grasp of electromagnetism is sufficient to design and build it. We don't need absolute philosophical clarity to make wheels turn, lights glow, or data move. Well enough is enough. This becomes especially relevant when people ask questions like, why do magnets attract? Often the expectation is an answer framed in familiar terms. Tiny rubber bands pulling things together, invisible springs, or some kind of hidden mechanical connection. But that expectation is backwards. Magnetism doesn't need to be explained in terms of something more familiar. Magnetism is the familiar thing. You just may not have recognized it as such. Every time you've touched anything in your life, you've felt electromagnetic forces. When your hand presses against a surface, the electrons in the atoms of your skin repel the electrons in the atoms of the object. That repulsion is what gives matter its apparent solidity. You never truly touch anything in the classical sense. What you experience as touch is electromagnetic interaction. The same force responsible for light, electricity, and magnetism is also responsible for the firmness of a chair and the resistance of a wall. We tend to separate these phenomena in our minds. Light over here, electricity over there, magnetism somewhere else. But nature doesn't make those distinctions. They're all manifestations of one unified force. You've been immersed in electromagnetism your entire life, swimming in it without realizing it. The colors you see, the textures you feel, the objects you interact with, all of it arises from electrons exchanging photons according to a small set of fundamental rules. So when someone asks why magnets attract, the honest answer isn't a story about hidden strings or unseen hands pulling them together. The answer is that magnetism is one of the basic ways the universe works. It doesn't reduce to something simpler. It's already at the foundation. And the fact that we can describe it mathematically, test it experimentally, and use it to build the modern world is one of the greatest achievements of science. We may not understand everything. We may never have perfect mental images of what's happening beneath the surface, but we understand enough, and that understanding has proven itself again and again in the real world.